No. Yes? Yes. I think it works.
Bır.
Finally. That's what I said. Okay. Chair is coming. Good morning, Professor. No worries. Yeah. Welcome. Here we go. So I think chairs should sit here, please. Yeah, sure. It's your place. I'm gonna take this one. So this is yours. So microphones works the following way. So what is you can try. This is some technical problem. It's good.
The problem is that I want to draw on the lap on the iPad. No, but on the iPad. Yeah, but
Connect with the Google Meet iPad and it shows your screen sharing presentation.
oh, but it works. It works now. Okay, then. Fine. Good.
Okay, good morning. This is Toru Ozawa. Sorry to have kept you waiting, and everything seems all right. And it's my great pleasure to introduce Professor Martin Heyer. The title of his talk is Top Lyapunov Exponent for Advection Diffusion.
Okay, thank you very much. Sorry for the technical hiccups. Thank you very much for the invitation. It's really a pleasure to be here. It's my first time in Central Asia. What I want to talk about today, it's based on two works. One of them is joint work with Michele Cottiselati from Imperial, and the other one is joint work with Sam Panshin-Smith from Tulane, Tommaso Rosati from Warwick, and Jae-Yoon Yi, who's my postdoc at EPFL. And both of them, so what links these two works is the following motivation. So it's a old work of Jonathan Mattingly and myself, where we looked at a model of turbulence, which is kind of very similar to the model that Alexei mentioned yesterday, except that here we took a two-dimensional torus, and our forcing is stochastic, except that we think of the stochastic forcing as really being an external forcing that kind of maintains the fluid in a non-equilibrium kind of steady state, not some kind of very weak molecular forcing, but kind of strong external forcing. And the difference is that instead of being very small intensity and kind of white noise, where you act on all frequencies in the same way, like what we saw yesterday, here you think of the noise as being sort of acting on essentially mostly one frequency, like the spectral density should have some kind of a peak or something like this, and then it's weak noise in the high frequencies. And what we showed at the time, so that was 20 years ago, was that under kind of very weak assumptions on the noise, you have a unique equilibrium measure. But of course, the assumption that we had on the noise was essentially that there shouldn't be any trivial invariant subspace. And so what I mean by trivial invariant subspace is you could imagine that, for example, take your torus and now think of it as actually being kind of 4 copies of a torus of half the size, and imagine that you take a forcing which actually has the periodicity of the small torus. Okay, so say if the force does something here, it does exactly the same here, here, and here. Right? So you make the forcing periodic but with half the period. And then obviously, if you start with an initial data that itself is periodic with half the period, then it's going to stay so for all times, right? So you have an invariant subspace here, which is the space of all functions that are periodic with half the period. And then, you can show that on that invariant subspace, you have a unique invariant measure. And the question is what happens in general. So what you would expect is, so now things depend actually on the viscosity, or if you want, on the Reynolds number in yesterday's terminology, because at low Reynolds number, so that's like high viscosity, so if your fluid is more like honey, then one also knows that one has kind of a one force, one solution principle. So you can so as long as the forcing is not too strong, you can start with any two initial data, And you know, if you run the solutions with the same forcing, but different initial data, the two solutions are actually going to get closer and closer to each other, right? So that's exactly like when you take a pot of honey and you stir the pot, right? Then you basically see the motion of your spoon still in the shape of the honey, right? So you kind of just see, you know, the last 2 seconds of the motion of your spoon. And if you do, you know, wait for a bit and then do the same motion again, you're going to kind of see the same thing. Whereas if instead of honey, it's, you know, like the cup of tea that we saw in the movie yesterday, then as Alexei explained, well, there you can, you know, you do your stirring and something happens, and then you do the same stirring later and then something completely different happens, right? And so you expect to have some kind of transition as you go from low Reynolds number to high Reynolds number. And here, the way, so the corresponding, if you want, mathematical conjecture then would be that if you put yourself in this kind of situation where you have this fluid which you force with a forcing of half the period, then as the Reynolds number goes from low to high, at some point there should be a transition at low Reynolds number, so high viscosity, so like honey, you expect to have always just a unique steady state. And then at high Reynolds number, you expect that you have a bifurcation of another steady state, which itself is not periodic with half the period, but really sees the whole box, right? And okay, so both of the works I want to talk about are kind of motivated by this question. So we don't know how to prove this conjecture. Okay, so I just gave you a kind of relatively clear mathematical conjecture. If you wanted to be very precise, you would have to say something a bit more about exactly the shape of the forcing, but it should hold somewhat generically. And so in some sense, there are two difficulties here. And the two works I want to present, they address separately these two difficulties, but we don't know how to put them together to, you know. So one of the difficulties is to actually show, like here, there's some kind of stability to instability transition that you expect, okay? And so one way of formulating this is that there's some kind of Top-Lyapunov exponent that goes from negative to positive. Okay? And of course, you know, typically mathematically, it's maybe not very difficult to prove that Top-Lyapunov exponents exist, but they might be very difficult to say something about whether they're positive or negative, or, you know, usually you can get like upper bounds, but then, you know, if your upper bound is positive, that doesn't really tell you much. Right? And the second difficulty is that the problem is infinite dimensional, right? So you have somehow an infinite dimensional invariant subspace, and then you have another complementary infinite dimensional space, and you expect that complementary space to become unstable at some point. And so you have all sorts of, if you want, technical difficulty does arise from the fact that it's infinite dimensional. So the first work, so that's the work with Michele Cottizelati, is a sort of super toy model where it's the same super toy model that Lorentz looked at in 1963 with a similar motivation, right? Like he was saying, okay, and to understand kind of, you know, the dynamics of the atmosphere, it's a very complicated PDE, so I just replace it by the simplest ODE that has the same features, and that's this very famous Lorentz 63 model, you know, with the butterfly Lorentz attractor that you've all seen 1,000 times, so I'm not going to show the picture. And now, in the Lorentz model, there is a, okay, so here I've written the Lorentz equation for you. So remember that it has a similar structure to the Navier-Stokes equations in the sense that there's a linear part. You see, so like this part is linear, this part is linear, this here is linear, which is in some sense similar to the viscosity part of the Navier-Stokes equations. And then there's a quadratic nonlinear part, so this xy here and this minus xz here. And that's bilinear, just like the Navier-Stokes nonlinearity, and it also preserves the L2 norm, right? So if you write the d by dt of the L2 norm, so x squared plus y squared plus z squared, then this term gives you a minus xyz, and this one gives you a plus xyz, so it cancels out, right? So just like in Navier-Stokes, the Navier-Stokes nonlinearity also preserves the energy. Okay, so here sort of sum of squares is some kind of energy that the nonlinearity preserves. And then if you put yourself in the, so there are these different parameters, there's sigma, rho, and beta, and let's fix sort of sigma and beta to the same as in the usual Lorentz system, but the rho is usually set to, I don't know, 20 something. But if you make it less than 1, then the system is really more like kind of unforced Navier-Stokes in the sense that 0 is globally stable. Okay, so then just like Navier-Stokes, if you take unforced Navier-Stokes, you start with any initial data, it actually goes exponentially to 0 just because of the Poincare constant if you're in finite volume. Okay? Say if you start with average 0. And here it's the same thing. So if rho is less than 1, then the same thing happened. The dynamic is very boring. You start from anywhere in R3, it just goes to 0 exponentially fast. Okay? And then there is an invariant subspace here, which is that if you start at x equal y equals 0, so if x is 0 and y is 0, then you see this term here drops, and in z you just get a linear equation. Okay? And so what we do is we add a random force, so this psi here denotes white noise, so just white noise in time, of strength alpha, and you see, I put this random force only on the z-axis. And so now what happens is if you start on this z-axis, so the z-axis is x equal y equals 0. If you start on the z-axis, then you stay on the z-axis for all times, because this term just drops. Right, so you don't see this term here. And what you see here is just an Ornstein-Uhlenbeck process. Right? You just see a linear equation with stochastic forcing. And that, of course, has a equilibrium measure, which is just a Gaussian measure. And then the question is, can you actually destabilize this, right? So now here, alpha plays the role of the Reynolds number. Okay, so that's sort of the strength of the forcing. And for small alpha, you know that the solutions, they don't go to 0, but they somehow all converge to each other. So there's a similar one force, one solution principle you can prove. And then the question is, can you destabilize this? So do you have a kind of bifurcation happening at some point for large alphas? Okay, so that's the question here. And here in this super toy model, you can actually answer this question. Okay, so in this case, you can actually prove that if alpha is small enough, then you have this one force, one solution principle, which is very easy to prove. But if alpha is large enough, then actually you have two invariant measures for this system. There are two different steady states. So there's one steady state, which is on x equal y equals 0, and then just the Gaussian measure, which is the steady state of that Ornstein-Uhlenbeck process. But then there's a second steady state that gives 0 mass to the z-axis, and that somehow gives otherwise positive measure to like every open subset of R3, so it's kind of fully supported in the space. And there is a certain value of alpha where you kind of bifurcate between these two behaviors. And so here is a numerical, so I'll just show you a numerical simulation. So this is what you see in the XY plane. Okay, so this invariant z-axis here would just be a point at the origin. And here the red and the blue trajectories are two trajectories where you take exactly the same parameters, the same initial condition. The only thing that you change is the value of alpha. Okay, so one of them the noise is stronger, one of them the noise is weaker. And you see that the red one is the one with slightly weaker noise, and it just goes exponentially to 0. Whereas the blue one, the one with slightly stronger noise, what happens is that it kind of, in the beginning it does the same thing, it kind of goes to 0, and then it becomes very, very small, but then occasionally, suddenly it makes these excursions, right? So you have these large excursions, and then it spirals back in, And then again, it makes a large excursion and it kind of spirals back in. So that's the kind of dynamic that you see. And the way you prove this, right, is, of course, you want to really understand here, if you want to prove that there is a second invariant measure, right, what's really important is the dynamic here and close to the origin, right? So you want to show that if you are very, very close to the origin, so the origin here is the whole z-axis, right? So it's x and y being small, but z not necessarily small. So if you're very close to x equal y equals 0, then you want to understand what actually happens, right? So you want to show that on average, you kind of, at some point, if alpha is large enough, on average, you actually get pushed away from that z-axis, okay? And so what you really do is you actually kind of linearize the equation, if you want, around that z-axis, which is not the same as just completely dropping the nonlinearity, right? Because you just think of x and y as being small, but z as staying arbitrary. And so here linearizing means that you drop this term here, right? Because if x and y are small, this term is quadratic, but you don't drop this term here, right? So because you think of z as somehow being like an order 1 time inhomogeneity, and then this term here, you think of it as actually being linear. Okay, so for fixed z, this is linear in xy. Okay, so now if you want, you view this as a linear system in xy, right? So if you think of z as being given, and z being given by simply d Ornstein-Uhlenbeck, where you drop this xy, okay? So if you think of z here as being given, then the system, the xy system, is simply a linear equation, but a non-autonomous linear equation, okay? And so then, if you have a non-autonomous linear equation, the natural thing to do is, instead of looking at the xy dynamic, you look at you put yourself in basically polar coordinates, right? And you say, well, the radial dynamic is essentially, if you understand the angular dynamic, then you kind of understand the radial dynamic as well, because what happens, so here I've written it here in polar coordinates, except instead of the radial coordinate here, it's more like the log of the radius, okay? So that exponential decay really corresponds to uniform, like unit speed or uniform speed motion, either to minus infinity or to plus infinity, okay? And so what you really want to understand is this angular motion, right? And so if you understand, say, the theta z process, so now the z process, again, it's just this linear, Ornstein-Uhlenbeck process. And then theta, well, it's just a, one-dimensional random ODE. And so theta and z together, they have some steady state. Okay, so there's some invariant measure for the theta z process, and that's not very difficult to show that this is unique and exists and so on. And then you see that on average, r is just going to move at a speed which is the expectation of this function here under the steady state for theta z. Right? So you have a somewhat explicit formula. Sometimes that's called the Fürstenberg formula for the kind of Lyapunov exponent. And the problem here, right, so what makes the problem kind of non-trivial is the fact that, well, now you want to figure out what the sign of this expectation is, right? So you see that you can think of, if alpha is very small, then z here ends up being very close to, okay, there's a change of coordinates here, so somehow the origin is no longer 0, but it's z star. It's just to make the equations look nicer. So you see, if alpha is very small, then z is going to be very close to kind of z star. And then if z star is kind of small enough and alpha is small enough, right, then this is not going to be able to beat the -1. Okay? So then r dot is kind of negative on average. and that means that you just converge to that vertical axis. And now what you want to show is that if alpha is big enough, then this term here actually dominates and is positive on average, right? But that's not completely obvious because this term doesn't have a sign, right? Z doesn't have a sign, and sine theta doesn't have a sign either, okay? Now you can kind of still make a guess of what's going on, right? By saying that most of the time, if alpha is large, right? So if you're in the situation where you expect instability, then if alpha is large, then most of the time Z is very large, okay? And then it's either very large and positive or very large and negative, right? Basically, half of the time it's going to be very large and positive, half of the time it's going to be very large and negative. And now, if Z is very large and positive, what happens is that, you see, this equation here, if you think now of Z as being fixed, okay, so that's kind of cheating, of course, because Z evolves according to this Ornstein-Uhlenbeck process, but it turns out there's some kind of approximate timescale separation that you can exploit. And so you can kind of think of Z as being frozen. Okay? And if you think of Z as being frozen and very large and positive, then this equation here basically has one stable and one unstable fixed point. You see that here near the origin, this is like a 1 minus Z times theta square. So it has, you have some kind of dynamic where you have this kind of parabola and you have two fixed points, like one here. This one is unstable, this one is stable. And so if you start from pretty much anywhere, you're going to very quickly run to the stable fixed point. And the stable fixed point is when sine theta is essentially 1 over square root of Z, right? Because you want this whole thing to be 0. So you want Z times sine square theta to be 1. So theta is basically 1 over square root of Z, which means that here, this term here is essentially square root of Z, right? So if Z is very positive, then this here is essentially square root of Z, which is also very positive, okay? And then you get kind of pushed away from the vertical axis. Whereas if Z is very negative, then what happens here is that you see the right-hand side is then always positive, right? If Z is negative, then 1 minus Z sine square theta is always positive. And that means that the theta variable just always keeps on, running around the circle. It runs around the circle in a very inhomogeneous way because it's like very high speed when theta is away from 0, and then it slows down a lot when theta is close to 0. So it runs away around the circle in a sort of very ununiform way where it sort of slows down when it gets near 0 and then goes super fast around the rest. But on average, it kind of averages out to 0, right? So it does this in a more or less uniform way. I mean, it's symmetric under theta goes to minus theta, that motion. And so under this motion here, that sine theta actually averages out to 0. And so it means that if Z is very negative, this basically averages out to 0 and you get a minus 1 here, okay? And so it means that when Z is very positive, then you get pushed away from the vertical axis, but at speed square root of Z. And when Z is very negative, then you get attracted to it, but at speed 1, okay? And so since on average you're kind of half of the time very positive, half of the time very negative, it means that if alpha is large enough, on average you actually get pushed away. Because when you get pushed away at much higher speed than when you get attracted, okay? And so that's that's actually kind of what you see in these numerical simulations, is when you get attracted, it's like if you diagonalize this matrix, right? If you think of Z as a parameter and you just diagonalize this matrix, what you find is that if Z is negative, then the matrix has two eigenvalues that have sort of real part -1 and then non-zero imaginary part. That's why you sort of see it spiraling in, right? Whereas if z is positive, you have two real eigenvalues. So there's one very positive eigenvalue, very large eigenvalue, and one very small one. And that's why you essentially see it sort of going out, basically always in this direction, because this direction is, well, basically the eigenvector that corresponds to the positive eigenvalue, right, for large values of z. Because that eigenvector sort of rotates, but there's essentially one value of z at which the thing actually destabilizes. And so what you see is essentially the direction that corresponds to the eigenvector at that value of z. Okay, so that's the sort of super finite dimensional super toy model, which is the Lorentz attractor. And so here we can really completely answer the original question that we asked ourselves, but okay, it's really a toy model, it's not a PDE model. Right? So now you would like to do something in infinite dimensions. And in infinite dimensions, like the kind of analysis that I just showed to you, is essentially not really doable. I mean, this was way too explicit for anything that you can do in infinite dimensions. And it turns out in infinite dimensions, there's already a much more basic question, which is interesting, which is just, you know, take some interesting, I'm going to show you an example of interesting, at least in our opinion. So take some kind of interesting non-autonomous linear PDE, okay? And then ask yourself even, does it even, you know, do you even have a lower bound? So like, is there a rate at which it goes, maybe it goes to 0, maybe it doesn't go to 0, either it goes to 0 or it goes to infinity. And usually it's not so hard to get an upper bound, right? To say that, okay, it doesn't go to infinity faster than some exponential rate, or maybe a negative upper bound, which says that it goes to 0 faster than something, right? But that doesn't rule out the fact that things actually go to 0 super exponentially fast. Okay? And the reason why this is not so easy to rule out is because in infinite dimensions, if you think of your PDE as being some kind of parabolic PDE, like, you know, Navier-Stokes, if you think of the linearized Navier-Stokes equations, then that's a linear time inhomogeneous PDE, okay, which is driven by the solution to the stochastic Navier-Stokes equation itself. And, well, it's a parabolic equation, so the linear part is just the heat equation, right? And now if you take just the heat equation, right, then it can go to 0 arbitrarily fast, depending on what initial condition you start with, right? If you start with a Fourier mode, if you start with sine of kx, and you stick this into the heat equation, well, it gets multiplied by e to the minus k squared t. And k can be as large as you want, right? And so the speed at which it goes to 0 is actually not bounded from above, because sort of depending on the initial data, you can go to 0 as fast as you want in the case of the heat equation, okay? And so the question is, can you rule out that kind of behavior happening generically? So here, let me just show you a simulation here as well of the sort of thing I'm talking about. So here, what you see is so that's a simulation that was done by Sam, Punch and Smith. And what you have is I think on the left, right, so on the left, you have a simulation of the two-dimensional stochastic Navier-Stokes equation. So it started, at the beginning, it started with initial condition 0, but you have a non-trivial stochastic forcing. So it usually, you know, it's two-dimensional turbulence, so you tend to have kind of some of this sort of pair of vortex, anti-vortex forming. And then on the right-hand side, what you see is the evolution of the linearization. Okay, so it's the derivative of the solution with respect to initial data. Okay? And then that on the right is the solution to a linear equation, but it's a linear equation that's driven by what's on the left. Okay, and on the left is just a solution to stochastic Navier-Stokes, which is very nonlinear. Okay, and then the question is, like if you look at the thing on the right, do you have a lower bound on the speed at which it goes to zero? So here things are kind of normalized in such a way that things are always appear to be the same size, roughly, right? So, so here, I guess what's shown is vorticity, which is a scalar in 2 dimensions, and then positive is blue and negative is red, and somehow the darker, the stronger. And things are rescaled so that the L2 norm, right? The equation on the right is linear, so you'd expect it to go exponentially either to infinity or to 0, and so you rescale it so that the L2 norm always stays 1. So you look at what we call, say, the projective process, right? So you look at the linear equation, but you project it on the sphere always, right? That's the analog of the angular. Remember, so in the case of the Lorentz attractor, we also had this linear system that was driven by an Ornstein-Uhlenbeck, and the linear system, it was a good idea there to write it in polar coordinates and to just look at the angular variable, and then the behavior of that tells you what the radial variable does. So here the analog is you have that linear PDE, time inhomogeneous, and what you look at is actually you project it on the L2 sphere. Okay, so you take the solution at time t, but you divide it by the L2 norm of the solution, so then by definition it has L2 norm 1 always. And then you're interested in the dynamic of that process. Okay, so then that process again becomes nonlinear, right? I mean, look, it lives on the sphere. Okay, and here what you see like morally, since it satisfies a parabolic equation, we think that the speed at which it kind of goes to 0 is roughly going to be given by something like 1 over typical length scale square or something, right? Because you have a Laplacian. Laplacian is essentially like 1 over a length scale square. And so the linear part, so here you have these kind of quite small length scales that are forming, right? So you see that the motion, this circular motion, it creates, these shapes. So it's a little bit like kind of kneading filo pastry or something. So you have these elongated filaments that form. And so you see you have sort of relatively small scales that form there. And so then the question is, at which point is there kind of a balance between these scales and the dissipative mechanism and sort of the viscosity, right? So if that balance sort of never happened, right? If these scales were to get smaller and smaller, then that would suggest that you actually go to 0 faster and faster, and then you would have no exponential bound from below, okay? So that's the kind of question that we ask ourselves. Right, so that's the thing that I already mentioned, which is that like even like in the case of just the simplest case of just heat equation, it's simply not true that you have a uniform bound from below on the speed at which you go to 0. Okay, and like one way of seeing that is that if you take the heat equation, you look at this projective process. So you take solution to the heat equation, but then you divide it by its L2 norm, so that you view it as a dynamic on the sphere. Then every single eigenvector corresponds to a saddle point or a critical point. Like the lowest eigenvector is somehow just an attractive fixed point, but everything else is a saddle point. And so you have these sort of infinitely many saddle points that correspond to the infinitely many eigenvectors for the linear operator, right? And so the problem here is then to show that your projective dynamic doesn't get stuck in these infinitely many saddle points, right? Okay, so here the actual example that we look at is not, so we did also look at the linearized Navier-Stokes equation, which corresponds to the simulation that I gave you, but and it has a very similar structure. But the example I want to show today is that of, oh, okay, sorry. Not sure what happened here. Okay, somehow it seems to have lost the connection to the iPad. Well, it lost the connection. Well, I can, yeah, but I can also. Just do it like this. Well, it doesn't work. But yeah, I know that, but this is not what I wanted it to do. But anyway, okay. So let's just continue on the laptop. But then maybe I need the clicker. Okay. Does the clicker not work? The clicker doesn't work either. No, it needs to go here. Okay. Okay, can you try to make the clicker work? And then okay. Anyway, right. So sorry about that. Right. So we looked at. What we do is we look at a passive scalar that's advected by the stochastic Navier-Stokes equations. Okay, so you take the stochastic Navier-Stokes equations, that's the actual model we want to look at, and then you take a scalar. So just think of it as being, well, like the milk in the movie yesterday, or say a blob of ink or something like this, that just gets moved around in your fluid. And it can itself diffuse. Okay, so there's two different viscosity constants here, right? So there's the nu, which is the actual viscosity of the fluid, and then there is the kappa here, which is the diffusion constant of the scalar or the tracer that moves inside the fluid, right? So the tracer is, on the one hand, it's advected by the fluid, on the other one, it itself diffuses inside the fluid, okay? And so these two constants have no reason to be the same. Okay? And so here one interesting regime is the one where all the constants for the fluid are for the one, but the diffusion coefficient for that scalar is very small. Okay, so you think of that kappa as being very small. And then the question here is, well, can you show, if you look at your W and say you make it average 0, so you can always subtract the average. So you make it average 0, then you know that it's going to go exponentially to 0, at least at speed kappa, right? Because just by the Poincaré constant, if you write down, the time derivative of the L2 norm square of W, it's equal to minus kappa times the L2 norm of the gradient of W square. And then by Poincaré, the L2 norm of the gradient square is bigger than the L2 norm square, and so you get an upper bound of minus kappa. Okay, so you go to 0 at least at speed e to the minus kappa t. And so the question that we had here is, can you actually get a lower bound, right? Like a, or it could go to 0 much faster than e to the minus kappa t. So in fact, it does go to 0 much faster than e to the minus kappa t. So there's an upper bound, there's a prediction, which is, so the prediction was, given by Batchelor back in the days. So now it doesn't even move anymore here. The whole thing's completely broken. So I'm not sure what's it actually showing now, because somehow it shows neither the, yeah, but it doesn't show the screen anymore. So this doesn't move anymore. Okay. Right. Okay, let's hope that they manage to fix it. They've got 5 minutes to fix it. Right, so it was predicted by Batchelor that the length scale, right? So if you look at remember in the movie, you have these kind of small filaments that form, okay? So the prediction was that the width, the typical length scale of these filaments, sort of the width of these filaments, is of order square root of kappa, okay? And so that means that the Laplacian of W itself should be actually of order 1 over kappa. And so in the, if you actually write down, the balance, so if you write down the derivative of the L2 norm square, this kappa times gradient W square should actually be of order 1. Okay, because the gradient, if the Laplacian of W should be of order 1 over kappa, the gradient should be of order 1 over square root of kappa, but gradient square should again be 1 over kappa, okay? And so you actually expect to have an upper bound that doesn't go to 0 like e to the minus kappa t, but like e to the minus t, constant, independent of kappa, okay? So it actually goes to 0 at the speed that's independent of kappa. And that's a result that was proven about 4 years ago by Bedrosian, Punch-and-Smith, and Blumenthal. Okay? So they showed that indeed you have this upper bound, which is of order 1, rather than of order e to the minus kappa t. Okay? And so what we wanted to do is get a corresponding lower bound. Right? So unfortunately, we don't have a lower bound that matches the upper bound that they obtained at the time. Okay, so we cannot get a lower bound that matches Batchelor's scale or Batchelor's prediction. No, it doesn't. It doesn't show the screen. It shows something else. It's just stuck on the. I mean, it doesn't get the signal. This is just stuck. This has nothing to do with what's on the screen. So I think the problem is up there, right? Because it just doesn't transmit anything. Okay, so the lower bound that we get, so which, well, I wanted to show, but it doesn't show anything. So in the end, we can show that you get a lower bound of the order, so the length scale, instead of having kappa to the, what you expect is kappa to the minus, well, kappa to the 1/2. So you expect the Laplacian to be of order 1 over kappa. Okay? So we can get a lower bound of order kappa to the minus 2. Okay? So which means that the Laplacian would be of order kappa to the minus 4. So there's an upper bound, if you want, of order kappa to the minus 4 on the Laplacian. And so that gives a lower bound of the order e to the minus kappa to the minus 3t, I think, or something like that. I mean, I had it on the slides, but I'm not sure I can make up the exponents like without the support of the slides. But we have a lower bound, which is of the order e to the minus some inverse power of kappa times t. And in some sense, it doesn't really matter what the inverse power of kappa is, because what you expect is to have no power at all, okay? But we can get an explicit inverse power of kappa. And I think with our method of proof, it's not clear one can improve on that exponent. And, well, I can try to explain sort of like why the proof is not optimal. Like, why don't we actually get the Batchelor prediction in the lower bound as well, okay? So how do you get a a bound like this, right? So what you want to do is you need to somehow get control on this projective process, right? Because in exactly the same way, so, you know, you can just write down the energy balance, right? And on the right-hand side, you have this kappa times the L2 norm of the gradient. And so you want to know that you want to get some sort of reverse Poincare inequality, right? So you want to say that on average, the L2 norm squared of the gradient is actually smaller than some constant times the L2 norm squared. Okay, so that's what you want to get. And that's the same as saying that if you look at the projective process, which is just the process itself divided by its L2 norm, then that process you want to get some bound on its H1 norm. Okay, so you want to get a bound on the H1 norm of this projective process, and you want to get a bound which is independent of the initial data, right? So even if you start your scalar with very, very small scales, then you want to show that actually, you know, after a while, you also have kind of larger scales developing. Yes. Right, like, so here you have to kind of exploit the nonlinearity, right? Like if you, because as I already explained, right, if it was just following the heat equation, then you start with very small scales, it stays like that, right? No, well, yeah, but this thing doesn't work, so the clicker doesn't work either. So. Okay, at least it does this, but somehow the clicker doesn't work. Okay, but now, okay, so at least you can see the statement of the result now. Right, okay, yeah, so I actually got the exponents right. Okay, so we have this upper bound on the H1 norm of W, so W is the passive scalar, divided by the L2 norm of order kappa to the -2, right? So this is some sort of reverse Poincare inequality, right? You have an obvious sort of lower bound of order 1 on this, right? Because the H1 norm is bigger than the L2 norm, so you have a lower, Poincare gives you a lower bound, and here you get an upper bound, but the upper bound depends on this diffusion constant kappa, okay? And in terms of actually previously known kind of lower bounds, basically the best we could find in that kind of setting was a double exponential lower bound, right? So it was a lower bound which is not of the form e to the minus some constant times t, but of the form e to the minus constant times e to the t. And so, okay, yeah, if you can switch. Okay, so that double exponential bound, so that's a paper from Miles and During from 2017, where if you switch, right, so you can basically, you just write down, you know, you write down the time derivative of this H1 square divided by L2 norm square, and you find that you get an upper bound on this time derivative, which is of the order of some derivative of the velocity field, right, sort of the driving vector field. And then you think of that as being stationary, so you think of this as being something of order 1, and you can essentially just integrate that equation and you get that double exponential lower bound. Okay, so that's a relatively easy, it's a sort of one-page calculation, so it's a somewhat straightforward calculation, which is not the main content of that paper, but it sort of happens to come out in their calculation, which is obviously really bad, right? So like this is not the thing that you want. You can switch and again. Yeah, well, okay, here I wanted to draw a picture on the iPad, so that's not going to work. So the main idea of how we control the H1 norm. So remember, like, the problem is that if you get stuck in the high Fourier components, right? So if you get stuck, that's what you have to fight against, right? There's all these critical points for the projective dynamic of the heat equation, where all the Fourier modes are just critical points for that. And so you can kind of get stuck in some very high Fourier mode, and you have to show that you get unstuck. And so the idea is that you look at the Fourier spectrum. Since you look at the projective process, by definition, it has L2 norm 1. Okay? And so the Fourier spectrum is actually a probability measure. Right? So you just look at the modulus squares of the Fourier coefficients. That gives you a probability measure on wave numbers. Okay? And now you just look at modulus of wave numbers. So it gives you a probability measure on R+. Okay? And now you want to show that this probability measure doesn't stay too concentrated, right? You want to show that that probability measure in some sense sort of moves inward, right? Because you want to show that you don't get stuck somewhere out in the very high frequencies. Okay, so that's how you get a sort of reverse Poincaré, right? I mean, you need to show that you don't get stuck in the high frequencies. And so what you do is you actually look at the dynamic of the median of that probability measure. Okay, so you look at the spectral density, you view this as a probability measure, and then you look at the median, which is the value, so that half of the L2 norm is supported in the Fourier modes above that value, and half of it is in the Fourier modes below that value. Okay? So that gives you some kind of length scale, or inverse length scale, if you want. And then you're like, well, if you have control over that length scale, well, then you can believe me that, well, basically, because of the equation being parabolic, in some sense, once you have a length scale, then you can turn one definition of a length scale in another one, right? So if you can get control on that median, it's not very difficult to also get control on the H1 norm. Okay, so the difficulty is to find some definition of a length scale and to get control over it. Okay, and it turns out that in this problem, if you go, it works now. No, it doesn't work for me. Okay. And right, so you want to get control over that median, and then the remark is that in fact, in this problem, that median gets smaller remarkably fast. Okay, so in fact, you can show that in some sense it's very close to following the ODE, just dtm equal to minus m squared. And that, you know, that you can start from anywhere you want, right? After time 1, the solution is at 1, or something like that, okay? So in fact, the median, it comes back towards finite sort of a compact set incredibly fast, like at speed. Like you can start from anywhere you want, and after time 1, you're in a compact set. Okay? So then if you can really show that, then you're basically done, right? Then you get very good control, and you get a control which is of the form that you can start with any initial data you want completely uniformly in the initial data. After time 1, you have control on the H1 norm of that projective process in a way that's completely uniform over initial data. Right? It's not even in a way that somehow depends in some complicated way on it. Okay. So how do you kind of show that the median sort of comes back at this very high speed? So essentially, okay, so the way in which, you know, I told you it sort of satisfies that ODE. So what do I mean by this? Of course, it's kind of a discrete, right? It only takes discrete values for starters. In some sense, it's not even well defined because your measure is atomic, and so, you know, and so it's going to kind of make strange fluctuations all the time. So you cannot just write down an ODE for the median, right? So it's in some sense, it's a slightly strange observable to take, right? Because it's not something that you can naturally differentiate in time even. Okay, but what you do is you sort of look at it at various discrete times. So you say, oh, I start with some very high value for that median, and then I look at the first time at which it goes down by 1, and I want to show that the time it takes to go down by 1 is typically roughly of the order of 1 over m squared. Right? So if the time it takes for the value to go down by 1 is about 1 over the square of the value, that means that you're essentially satisfying the ODE, dtm equal minus m square, right, in some sort of discrete sense. But in particular, because 1 over m square is summable, that tells you that in finite time, you get back to finite values wherever you start from. Okay? And so the way we prove this is first, so in the first step, we show that if you look at a time of order 1 over m square, then there's some positive probability that some Fourier mode of order 1 becomes sort of non-zero, right? But very small, right? So we get some kind of lower bound of this order m to the minus gamma, where gamma is some relatively large exponent. So it says, you start from some super high value of m, and then you look at one of the Fourier modes, one of the order 1 Fourier modes. Okay, so like just the first Fourier mode or the second Fourier mode. And after this time of about 1 over m squared, there's a positive probability, so it doesn't happen for sure, but it's sort of an order 1 probability, that what you see is a non-zero value which is of order at least m to the minus gamma. Okay, so at least some very tiny value. Okay? And then that sort of gives you, in order to show this, you need to really use the kind of nonlinear interaction between your scalar and the fluid, and you use the stochastic evolution of the fluid, right? So remember that the fluid, like the Navier-Stokes equations, we assume that you have some stochastic forcing on it. And so that's what allows us to show, well, so first that's why you get probabilistic statements, but that's also what allows us to, in some sense, not worry too much about what's, for example, the current state of the fluid, okay? Because we know that you have this stochastic forcing that acts on the fluid, and so it gives you some randomness to play with. Okay, so you have kind of new randomness coming in all the time. And okay, so you can get this kind of, with some probability, a tiny bit of energy in the low Fourier modes. Okay, and so for this, what you do is you essentially do right, you have parabolic, semi-linear parabolic equations. You can do a short-term expansion, right, by essentially doing a couple rounds of Picard iterations and then looking at the remainder. And then, because you have this linear stochastic forcing, the first term in that short-term expansion is actually just a Gaussian random variable. Right? And then you can just basically compute the variance of this Gaussian random variable. Right? So you look at simply the lowest order term for your solution for the scalar in which you see the effect of the stochastic forcing, and that's just going to be a Gaussian random variable, so you can compute its variance. And then you need to show that, the remaining bits don't drown this. And then, of course, if you do it naively, that doesn't work because the remaining bits appear to be much larger, but then you do a sort of third order expansion instead of just first order, and then, those terms you can still bound them by using tricks, using the explicit form of the terms, and then you have a remainder which is kind of small enough so that you can say it doesn't matter. Okay, so there's some fiddling around, but you can show that a little bit of energy gets moved into the low Fourier modes with some positive probability. And then you say that if that happens, then you can exploit the fact that the equation is dissipative, right? So if you have a little bit of non-zero mass in some low Fourier mode, and most of the mass, right? You think of m as being super large. That means that half of your L2 norm is at Fourier modes bigger than m, which is very, very large. If now you look at an evolution for a short time, the heat equation is just going to knock down these very large ones, and it's essentially not going to touch very much the low Fourier modes. And so after a very, very short time, the relative size of these two components has changed drastically, right? And so you can show that like, if you manage to have some tiny amount of energy in the order 1 Fourier modes, and m is very, very large, then after a very short amount of time, the median has to move down by 1 simply because the relative size of these low Fourier modes has increased by a lot, and that's sufficient to kind of shift the median downwards. Okay? And then you say, well, okay, so this thing only happened with some possibly very small probability, but then if it failed to happen, you essentially restart. You use sort of the Markov property to allow you to kind of restart your bounds. Of course, what you need to do is you need to somehow be able to control what's happening, right? Like if the median failed to go down in that short amount of time, or say if you failed to transfer some energy from the high Fourier modes into the low Fourier modes in that short amount of time, you need to make sure that that failure didn't somehow cause the median to go up even higher or something to completely mess up your system, right? But it turns out that you can kind of keep that under control, and so you can iterate this argument to say, well, if it failed to happen the first time round, since there's kind of positive probability of this happening every time, you essentially get kind of like a geometric random variable, which then very quickly is actually going to happen, right? So that's kind of the idea of the proof. So so I stop here, just give you a couple open questions. I mean, of course, right, sort of like the main open question in this bachelor scale business here would be to actually match the upper and lower bounds, right? So like we get this bound of order kappa to the -2 on the bachelor scale. So an upper bound on the bachelor scale of order kappa to the -2. There's the lower bound obtained by Bedrosian, Punch, Smith, and Blumenthal of kappa to the -1/2. And of course you would like to, and you know, the expectation is that the lower bound is the correct value. And so one would like to be able to decrease that upper bound to also reach -1/2, maybe modulo log terms or something like this. But that, you see in the idea of proofs, like what's the problem? The problem is that we use the nonlinear interaction only at a sort of very short times in order to show that there's some non-zero probability of kind of moving energy into the low modes. And except for that, we try to get as much mileage as possible out of the linear part of the equation, right? Which to some extent you have to fight it because it gives you all these critical points, but then you try to get as much mileage out of it as possible. In reality, you would like to somehow exploit much more the nonlinear part of the dynamic, right? I mean, in the sense that since kappa is very small, the natural thing for your dynamic is to expand it not around the solution to the heat equation, but around the solution to the free transport equation, right? The transport equation without diffusion, right? What the solution really does is it basically gets transported, and then it does a little bit of diffusion on top of this. And we mostly try to approximate this at very short times by doing these pk iteration, but the pk iteration essentially approximates, it does a sort of expansion around the solution to the heat equation. And for very small kappa, that's in principle not a very smart thing to do, right? Because the short time evolution is actually dominated by transport and not by diffusion. So it's only in the very, very high scales that it's dominated by diffusion, okay? And that's why then we cannot get down below scale of order kappa to the -2, which is sort of a very large, a very large wave number, okay? Okay, and then, well, the other open question, of course, is the one that I mentioned at the very beginning of the lecture, right? So like this was motivating these two works that I told you about, and they have a similar structure. Of course, it would be really nice to have a result, you know, which shows that for 2D Navier-Stokes, you really have a transition where you kind of destabilize these stationary solutions as the Reynolds number goes from kind of small to large values. Okay, okay, thank you very much.
Okay. Thank you. Are there any questions or comments? Mm-hmm. Okay.
Okay, thank you very much. My first question is about the first part of your talk, right? When you mentioned the toy model. My question is the following: whether or not it's necessary to identify the value of alpha when you pass from the uniqueness of the invariant measure to the non-uniqueness. If it's necessary to identify this value alpha, right? Because for alpha small, then you show, right?
Right, yeah,
Uniqueness
so we don't have a, okay, so the thing is that what we show is that, okay, so it's not very difficult to show that if the top-Lyapunov exponent is positive, then you have non-uniqueness, and if it's negative, you have uniqueness. But we know that for small alpha, the top-Lyapunov exponent is negative. For large alpha, it's positive. We don't know that it's monotone. Right? So the top-Lyapunov exponent as a function of alpha, in principle, it could increase and then decrease and then increase again. And so you could, in principle, have several transitions. And that we cannot rule out. Numerically, of course, you only see one transition, and it seems monotone. But there is no obvious monotonicity in this problem. And so we don't actually know whether this is monotone. And so this is why we don't have an actual theorem that says there is a value alpha star so that above you have non-uniqueness and below you have uniqueness, right? Because you could, in principle, switch more than once. You can also guess the value in the sense that you have this system which is given by theta and z. And then you have an explicit formula, which is somehow like the integral of this whatever function I showed. Maybe I can show it again. Right, so here you basically just look at this, right? So like there's this function minus 1 plus z over 2 sine 2 theta that would have to be integrated against the stationary measure of the theta z process. And then when it's positive, you have non-uniqueness. When it's negative, you have uniqueness. The problem is you don't have an explicit formula. Like the theta z process is not reversible or anything. You don't have a formula for its invariant measure. And so you can kind of approximate it. So remember I gave you that argument that says that in some sense, this f of theta z should roughly behave like kind of square root of z for positive z's and basically 0 or like minus 1 actually for negative z's. You can make a slightly more precise version of that. And then you can just replace f by that. And now it's only a function of z. And the z process, you know that the stationary distribution is just a Gaussian. So then you can compute everything. And that gives you a guess for the value of this transition. And in the numerical experiment that I showed you, if you do that guess, it agrees with the numerics to about 1%. Okay, so it's actually very close. So this is really a good approximation, actually, even though there isn't really a timescale separation or something, right? So this is a cheat. There's no theorem. In some sense, the proof goes through showing that this is a good approximation, but it shows that this is a good approximation only for very large values of alpha. But it turns out that even at the values of alpha, which are of the order of the point at which the transition happens, it's already a very good approximation. Okay, and it gives you like a 1% error if you compare to numerics.
Okay, thank you very much. And last question is when you show the model that you call the non-toy model, right? You assume decay of the Fourier transform of psi, right? And the decay is like something like k with the power minus 10, right? Because I am not familiar with the model. If this exponent minus 10 is the chart that you need for your analysis.
Is just okay. So this alpha bigger than 10 here. Okay, so that what that? Oh yeah. Right. So this is a choice for the forcing. So it's basically saying I want my stochastic forcing to be, on the one hand, I want it to be smooth. Right. So that's the alpha is essentially the regularity of the stochastic forcing, right? I mean, it says that the kth Fourier mode has a noise of strength k to the minus alpha, basically, right? And so then if alpha is large, then the kth Fourier mode has very small noise, and so it means the noise is kind of smooth. So you need it large enough just to get smoothness. So 10 is, whatever, laziness, right? I mean, there's no claim that 10 here is the optimal value or anything. It's just saying we want it to be smooth enough. But then one thing which is important is we also, on the other hand, we do want a lower bound on the decay, right? In the sense that we want enough forcing on all the Fourier modes. So we want some forcing on all Fourier modes. And that we really need in that argument, right? Because we exploit the forcing in order to get the randomness that allows us to transfer some energy from very high Fourier modes into order 1 Fourier modes. And that relies on some sort of high-high interaction between the scalar and the Navier-Stokes solution. And that means that you need forcing on those Fourier modes that you select for that high-high interaction, right? And so then it's sort of the easy assumption is to just assume that there's noise on every single Fourier mode and, with some kind of quantitative lower bound.
Since time is up, let's thank the speaker again. We are continuing the next plenary talk. So let's wait the next speaker.
working?
Okay, let's start the next talk. It's my honor to introduce Professor Nade Masmoudi. The title of his talk is Nonlinear Implicit Dumping.
Okay. Okay. Okay, so can you hear me? Okay. Okay, Assalamu alaikum. So first I want to thank the organizers for this very nice invitation. So I'm very happy to be here. So this is my first time in Kazakhstan. So I'll be talking about nonlinear implicit dumping. So I'll be talking about 3 works, one with Jacob Petrosian and another one with Yu Dang and with Weiran Zhao. Okay. So I don't have the, can I have the, okay, I don't know how to, where is the, okay, okay, thank you, okay, good. Okay, so first I'll try to, I know there are many students and maybe people interested in results about fluid mechanics. So I'll talk about what have been done maybe recently in mathematical analysis in fluid dynamic. So usually the kind of problems we are interested in, it can go from stability of very simple flows. So we heard talks related to this. So you have a simple flow and you want to understand when it loses stability. So then we have also question related to long time dynamic, what happens in long time, asymptotic stability. Then we can have phenomenon like implicit dumping. My talk will be about implicit dumping, enhanced dissipation. Then we have questions about transition between laminar and turbulent flows. Then we have all kind of limits when you have small parameter in your equation and you send this small parameter to 0. So then we have also questions about singularity. What happens if we have singularity? Can we describe singularities? And then with all these kind of results about fluid, one is really interested also in applying them to other equations. So I guess there should be a lot of interesting problems in trying to apply this to crowd, to traffic, and so on. So I'd like to start with some pictures to illustrate some of these ideas. Let's say when we talk about stability of a vortex, that can refer to this kind of pictures. So usually a vortex, so we say, okay, it has some kind of intrinsic stability, so that's why we can see this really huge tornado or hurricanes, like they are related to the fact that these kind of structures, they have some kind of intrinsic stability. The phenomenon I'll be talking about today is related to the idea of implicit dumping. I mean, this picture will come again, but it's really the idea that we can have some kind of damping even in cases where we have conservation of energy. So another picture which I like is this red spot on the surface of Jupiter. Again, this is a huge vortex on the surface of Jupiter, which has been there for centuries. Again, it's related to the kind of intrinsic stability of the vortex. Maybe I'll go fast on this. One thing I was mentioning is the transition between laminar and turbulent flow. This is also an interesting kind of picture where you can see a laminar flow that become turbulent. Mathematically and also like in terms of applications, the intermediate region, the transition region, is somehow more difficult to model, because for turbulent flows we have models. For laminar flow we know how to describe laminar flow, but usually the transition region is hard to model. So this is a famous kind of experiment going back to Reynolds, where we can see the transition between laminar and turbulent depending on the Reynolds number. These are also pictures that shows that this kind of transitions can happen, so it has some kind of intermittency. I will not be talking today with boundary layers, even though I have been very much interested in boundary layer separations. Okay, so my talk today, I'll start by talking a little bit about the Reynolds experiment. I will be talking also about 3D models and transition threshold, but this is just for the introduction, but my talk will be inviscid. Viscosity will only appear at the beginning, but later on I'll be talking mostly about 2D Euler. So the 3D is just for the introduction. And so this is the famous experiment of Reynolds. So this famous experiment of Reynolds came at a time where people were also trying to do some simple calculation about linearizing Navier-Stokes around this laminar equilibrium. And at that time there was some kind of paradox, because when you linearize Navier-Stokes, it appears to be stable at all Reynolds number. However, we are seeing this kind of transitions. And one can, of course, try to understand this kind of things even with the very simplest flow, which is, let's say, the Couette flow. One can look at the 3D Couette flow or the 2D Couette flow. So for today's talk, I'll be mostly interested in the case where X is in the torus and Y is in the whole space. So, but that's kind of the 2D Couette flow. So it's really the simplest kind of non-trivial flow, right? So the trivial flow will be 0. So you want to go one step above. So you want to have a very simple flow, but not the trivial one. That will be the Couette flow. And my talk today will be about understanding the perturbation of Couette. Okay. If I have, I like to keep it. Okay. Let me put the picture here of. So the Couette flow will have this form, y0, 0, right? So it is this kind, oh, okay. It's really this kind of flow. Okay. Can we go back to the slides? Okay. Yeah. So that's really the flow. So it is a stationary solution of Euler and also stationary solution of Navier-Stokes, and one can try to understand the stability of this flow. So you want to linearize around this flow. So you write down your solution V as the Quet flow plus U, where U is, let's say, a small perturbation. And then you write down now the equation on U, right? So you write down the equation for U. And it has two parts, like there is a nonlinear term and there is a linearization. So the linear terms are the linearization around Quet flow. And one way of getting around this paradox that I mentioned, the paradox comes from the fact that at the linear level we expect things to be stable, but in practice we see instability happenings. So in a sense, we are really at the boundary of stability and instability, right? And one way of solving this is to introduce the idea of stability threshold, meaning that you are given a Reynolds number and you are given a space, a regularity space, let's say capital X, and the question is to find a gamma such that if your perturbation is smaller than the Reynolds to the minus gamma, you get stability, whereas if your perturbation is bigger than the Reynolds minus gamma, then you can get a possible instability. Right? So this is one way of understanding the fact that we are at the boundary of stability and instability. Right? So in a sense, when the Reynolds number goes to infinity, so when viscosity gets smaller and smaller, the size of the perturbation which are allowed is shrinking, right? So that can be the reason why we have this kind of instabilities, even though at the linear level we see stability. So now the choice of the space X corresponds to how we measure the size of the perturbation. So it can be L2 norm, H1 norm. It turns out here some numerics suggest that gamma may depend heavily on X. In the talk today, we'll see spaces which are really of very high regularity. It will be like Gevrey spaces or analytic spaces. So there are a lot of works, both on maybe like 20 years ago. There are experimental works. There are also numerics. And different values of gamma appeared. In the physics literature, at some point, people were talking about two kinds of perturbation. They will call them smooth versus rough. There were smooth versus rough. Not necessarily Sobolev spaces like mathematicians like to put it. But there are different values of gamma. I will not go into that. But I can tell you, for instance, there's an important work of Romanov in the 70s. At that time, he has gamma to be like 4, but nowadays, like with we know that gamma should be more around 1. Remember, like the gamma, we want gamma to be, I mean, normally we want to have an upper bound and a lower bound. So normally the gamma is unique. But in practice, usually we are able maybe to prove the stability with one value of gamma, but the instability with a different value. So the whole thing is really to keep them, to get them to be the same. Okay. Let me just mention some of the works I've been involved in. So the first result here I'm mentioning is a result where we are able to prove stability in some kind of high regularity space, some Jouvray space, when the perturbation of the size Reynolds -1. So this perturbation of the size of the viscosity, then we are able to prove stability, but in Jouvray space. For the same notion of size, we are also able to prove instability if the perturbation is bigger than the size of the viscosity, right? So in a sense, A and B tells us that for that regularity space, gamma is 1. At that time, we were not able to lower the regularity to Sobolev. We were not able to lower the regularity to Sobolev, but the recent work of Shen, Wei, and Zhang, very interesting work, like they are able to prove that gamma is 1 even for some Sobolev kind of perturbations. So in a sense, the Jouvray regularity here is not really needed. The second kind of things, and here, right? Okay. So let me go to what I am more interested in, which is the D. So in this result, we are proving that gamma is 0. What does it mean, gamma is 0? It means that we are able to, so this is in 2D. So we are able to get stability for perturbations which are independent of the Reynolds number. So meaning that even when the Reynolds number goes to infinity, even when the viscosity goes to 0, we are still proving stability uniformly in the viscosity. So, which means that gamma is 1. But this result requires really the Jouvray regularity. So, in a sense, here we need the Jouvray regularity to prove the stability uniformly in the viscosity. And in a result with Yu Deng, that it was only published 2 years ago, we are able to prove the optimality of the Jouvray regularity. So in a sense, for this 2D result, to get perturbations which are independent of the viscosity, we really need the Jouvray regularity. Okay? Another extension of this result that I will be talking about is a result with Ver and Zhao, where we can prove similar result where we perturb not just the Couette flow, but any stable monotone flow. Right? So I will try to explain how we extend this result from perturbing Couette to perturbing more general monotone flows. Okay? So in a sense, this slide has more or less the three kind of result I want to mention. So again, the first one is the result where where we prove the stability of wet flow in 2D, stability of wet flow in 2D, even without viscosity. Okay, so we don't need viscosity for this result. If we are in the Gevrey regularity, and the Gevrey regularity here turns out to be optimal, meaning that if we are slightly below the regularity mentioned in D, then we can prove some kind of instability. So it shows the optimality of the regularity space. And then the last result is what happens if we replace wet by some stable monotone flow, how we can extend also the result to that case. Okay. Now, I'm not going to mention all the extensions that happened. I'll go very fast on many extensions of these works to what happened, let's say, around the vortex. I mentioned the vortex. There are also so there are the results about vortex, let's say, I want to mention, but also results about for different kind of flows, Kolmogorov flow, Poiseuille flow, other models. Many also, there's a huge literature now on studying different results. So I will not go into all these. There's also huge literature also on related works on Vlasov. So there is, starting with the famous work of Muho-Villani about Landau damping. Okay, so I'll start with talking about the 2D Euler, and in the setup where I am in the torus times R, right? So I am in 2D, so I am in 2D, and my domain is the torus times R. So X is in the torus, Y is in R, okay? Okay, and so clearly Y0 is a stationary solution. Y0 is a stationary solution, and I'm writing the equation also in the vorticity formulation, so omega is the curl of U, so the curl in 2D is just transported by the velocity. Of course, now for Euler, any shear flow is a solution. Any shear flow is a solution, and the particular case where U of Y is Y, that is wet flow. Now, one can linearize around the wet flow. If you linearize around the wet flow, that is the equation that you get. So it is linearly stable. It is linearly stable. It has no growing mode. However, we have to see that we are really at the boundary of the instability, right? So it's and the results we have here, they show that to get the nonlinear stability, you have to be really in this very high regularity space. You have to be in Gevrey space to prove nonlinear stability. Okay? So, okay, just so that we know what are the spaces we are talking about. These are the spaces I am interested in. Jouvre regularity. Jouvre regularity means that the Fourier transform decays exponentially, but it decays like exponential minus lambda k plus c to the power s. Okay? S equal 1, that will be the analytic regularity. S equal 1 is analytic regularity. Very nice exercise is to write down these things on the physical side. So you can understand this both on the Fourier side or in the physical side. In the physical side, it tells you how derivatives grow. Okay? So the space here, G lambda S has two parameters. The lambda plays the role of the radius of analyticity, right? So it's like some kind of generalized radius of analyticity. When S equal 1, it is exactly the radius of analyticity in analytic regularity. Like if you think that you are extending the function in the complex plane, that is the lambda is exactly the radius of analyticity. So the result with Bedrosian says that for the nonlinear problem, if we take a perturbation which is small in this Jouvre regularity, then the solution exists for all time and stays bounded. Stays bounded after you filter. We have to filter. There is a filtering that should happen. And I'll explain it. I mean, it is a simple feature of the fact that there is this kind of mixing. Of course, now lambda, you have to lose a little bit on the lambda. So you start with the lambda. I mean, but this is very natural for any result about analytic regularity. Always the radius of analyticity, you have to allow it to shrink a little bit. But not only the fact that we have this global existence and omega stays small, but we have the idea of implicit damping. Now, the implicit damping idea means that your omega will actually, in a right coordinate system, omega will converge to some f infinity. Okay, and now the feature, the implicit damping. Okay, 1 second. Right, and the phenomenon of implicit damping that I will mention is the fact that the velocity will be decaying. One component will be decaying like 1 over t, the other one will be decaying like 1 over t squared. So it will appear in the proof. Okay. Now the Jouvre regularity I have, S has to be bigger than 1/2 in my result, and the optimality of that comes from this result. So the result with Udang says that if it is possible to find a perturbation which is small, but in G lambda S smaller than 1/2, such that the solution will be large later on. So this is a kind of instability result, and it shows that it shows the optimality of the Jouvre regularity. Okay. Okay, I'll skip this, and let me mention the fact that some related work to this optimality, an interesting result by Lin and Zhang, 2010, who proved that there is no implicit damping in H3 halves. So, of course, there is a gap now between this H3 and the Gevrey regularity, and okay, that's still not very well understood, to be honest. Okay, let me start by talking about the parts of the proof. And the first very simple calculation, I mean, it's a very easy calculation, is to look at the linearization around Quet flow. So the linearization around Quet flow is the fact that omega is just transported, right, by the Quet flow. So then you can solve it explicitly, just the initial condition that goes through this kind of mixing. So, so of course we like making change of coordinates, and here if you choose z to be x minus ty, so I just choose z to be x minus ty, at the linear level, f is not changing. F is just the initial condition, right? So f is just the initial condition. And then if you write down the nonlinear problem, so the nonlinear problem will be the equation I'm writing there. So that's the equation satisfied by f. So it's just a nonlinear, it's only nonlinear term. Now the interesting feature of this is that this kind of mixing that's happening, how we see it when we try to look at the Laplacian minus 1, right? So, of course, now in, okay, maybe I should go back to Euler, right? Now, the Euler equation written in the xy variable has the Laplacian minus 1 grad perp. That gives you the velocity from the vorticity, right? That's in xy, in the original variables. But when you move to the z variable, so if I go to the zy variable, the interesting feature is the Laplacian minus 1 becomes this Laplacian t minus 1. So it's very simple change of coordinate exercise, but very deep for this problem, because the Laplacian t minus 1 has a t square in it, So meaning that this Laplacian t minus 1 will give you 1 over t squared decay. Okay? At least for if you have z dependence. For the z dependent part, there will be some 1 over t squared decay. And one can see it immediately on the Fourier side. You can you can write down the Fourier you can write down the Fourier transform of f, and you apply the Laplacian t minus 1, and you see in the denominator you have a t square. Now, to get this t square decay, there's no way of getting it without losing derivatives. And that's a very important feature of this problem, is that to get decay, you have to lose regularity, right? You cannot get decay for free. So to get decay, you have to pay regularity. And that's kind of the estimate you should have. Like, let's say you lose almost like 4 derivatives to get the 1 over t squared decay. And of course, now decay usually is good to get global stability, but as I said, you have to pay regularity. And I mean, the whole nonlinear result is to try to make sure that you pay exactly the right amount of regularity to get the nonlinear decay. So this picture, I mean, it's really rewritten from a paper of Orr. Orr wrote a paper 1907 mentioning this kind of decay, but also mentioning the idea that this decay can have some growth before. So we can have some kind of transient growth, and then you can have decay. So of course, now here you see Xc minus Tk, Xc minus Tk, but if you think that Xc and K, if you think that Xc and K have the same sign, you can see that the denominator reaches a maximum when T is Xc over K. The denominator reaches a minimum when T is Xc over K. It means that your solution grows and then decays. So you start, you grow, and then you decay. So that transient growth is very dangerous for any nonlinear kind of result you want to prove. Okay? And physically, it corresponds to unmixing. So you can think that you start with something which is mixed like this, then you have unmixing, and then you mix again. So this kind of unmixing, there's nothing, I mean, it can happen, and you have to control it. These are like physical experiments also capturing this kind of unmixing. Maybe I'll skip them. Okay. What I want now to mention is the extension of this result to general shear flows. So I'm not talking about nonlinear. I'm not explaining here why the Gevrey spaces appear and so on, but that's due to nonlinear interactions. But for today's talk, I want to more insist on the linear part. And the result I want to mention here is the result with Weyran-Zhao, where we have the extension from QET to general shear flows. So here I'm perturbing not QET, but I'm perturbing a general shear flow. Okay, so if I perturb a general shear flow, there is an extra term So I don't just have this kind of mixing with y dx like I had here. So you remember here, at the linear level, omega just solves a transport equation, right? And that's a very special feature of the QET flow, the fact that the second derivative of y is 0, right? But if you linearize around the general shear flow, there is an extra term in the linearization, which is that u double prime y dx of psi. Psi is the stream function, right? So, so what can one do with that extra non-local term? So we call it non-local because in terms of omega, it is non-local, right? In terms of omega, in terms of the vorticity, it is non-local because it has the stream function, and the way you calculate the stream function is by inverting the Laplacian, okay? So, so now let me mention this result about nonlinear implicit damping, but for general monotone flows. So the result goes like this. So we assume that U is monotone. Okay, so U prime is bounded from below. Here we are able to do it also in a bound. Y will be bounded. Y will be between 0 and 1. So we are in a bounded domain. We don't need the whole space. I mean, I remember when we first had these results in Y in the whole space, I had a lot of question about why Y is in the whole space, because it's unbounded and so on. But we are able to do it also in a bounded domain. But we need, not for technical reason, I mean for some serious difficulties, we need the flow, we need the U double prime, we need U double prime to vanish close to the boundary, close to 0 and 1. So when we approach the boundary from the lower and the upper boundary, it has to be looking like some kind of quet flow. And then we have another assumption, the fact that the Rayleigh operator has no eigenvalues and no embedded eigenvalues. So this is the stability of the flow we are linearizing around. And then we need some kind of Jouvray regularity assumption on the flow we are perturbing around. Okay. So then the result more or less says that the statement says more or less that we have exactly the same kind of stability result. Okay, exactly the same kind of stability result. I don't want to go into the detail of the statement, but we get exactly the same stability if our perturbation is in the Jouvray space. Okay. Here I'm also adding the decay, the implicit dampings, meaning that the first component of the velocity, after you remove the average, the first component of the velocity will decay like 1 over t. The second component of the velocity decays 1 over t squared. So these are what we call implicit damping. The implicit damping, that the fact that even though there's no viscosity, you are solving Euler, but still you have decay of the velocity. So that's what we call implicit damping. Okay. How much time I have? I mean, I don't know when I started, to be honest. So 10 minutes? Okay. 10 minutes. Okay. So so I should mention that there is a similar result by Ionescu and Gia, but in their result they don't have scattering. Here we have scattering, meaning that we are able to say that omega, after you filter, so there is some kind of modified scattering, after you filter the linear behavior, after you filter not just, I mean, it's some kind of non-linear behavior, like you filter, you have to remove the ty, but plus phi. So in a right coordinate system, omega will converge to some kind of final profile. Okay, so this will be, like for people familiar with dispersive equation, this will be some kind of modified scattering. Modified because of the phi. The phi depends on the solution itself. Okay. So let me now just tell you a little bit features of these new results. So what is some of the idea in this new result? So I'm not talking about the nonlinear part. The nonlinear part explains why we need the Jouvray regularity. I'm not talking about that, but I'm only talking about how the result has been extended from QET to general shear flows. Okay? And so basically, the main, I would say, the main difficulty of the general shear flow compared to QET is this non-local term, right? So the non-local term prevents us from using the transport equation to solve the linear problem. So in a sense here, when I have the non-local term, I don't have a very simple solution for the linear problem. And you can see in the case I was perturbing around QET, that was the main simplification. I mean, it allows me to write down the solution. You write down the solution, you can see how the stream function decays and so on. But if I have this non-local term, that is a major difficulty. Now, the idea is, I mean, inspired from, let's say, Schrödinger equation with potential. Like when we consider Schrödinger equation with potential, one idea that is usually used is the idea of wave operator. So wave operator is the idea of applying this operator that tries to get rid of the potential. Or here we want to apply this wave operator to get rid of the non-local term. Okay? So that's the whole thing. Is can we construct a wave operator that allow us to get rid of the non-local term at the linear level? Okay. Okay. So that's really what I want to show today. Of course, there are many other difficulties that come with the wave operator of how you apply it, then how it interacts with the nonlinear term. That I will not talk about today, but I will just show you how we get rid of the non-local term at the linear level. There are many other difficulties related to the nonlinear dynamic. So, so let's start with the linear dynamic. Okay, so that is just the linear equation. Okay, that's exactly the linear equation written in terms of the vorticity. So Laplacian psi is the vorticity. So then classical thing is you take the Fourier transform in X. Remember, X is in the torus, so you take the Fourier transform. So then it becomes some kind of an equation on dt psi, and psi hat is just a function of y. So one can invert the Laplacian. You can invert the Laplacian, so you can write down also the equation in terms of the vorticity, or in terms of the stream function. You can write down the equation in terms of the stream function, and then you get that equation. Okay, so I mean, in a sense, one can write down things in terms of the stream function or in terms of the vorticity. It's more or less the same. It's more or less the same modulo this commutation relation. So it's just applying the Laplacian minus 1 before or after, right? So, but like the two operators that you are seeing, the R alpha and the RU alpha, they have that relation between them. And then here we have to use the fact that the assumptions I made on u of y was stable, so I didn't have eigenvalues or embedded eigenvalues. Okay, so okay, maybe I'm going fast. Right. So again, I'm going to solve the equation about the stream function. I'm writing the equation in terms of the stream function. So that's the equation in terms of the stream function. Now one can represent the solution by this contour integral. Right? You can represent the solution by a contour integral. The omega has to go around the spectrum. Now the spectrum is just the image of u of y. I'm not going to go through that, but I mentioned here that all these stability assumptions that we have tells us that the spectrum of R alpha is just the range of u, and so then we can have that formula for the stream function by doing the contour integral. So in a sense, this is the picture. So you have a contour that goes around the range of u. Okay. So again, this is classical thing about in function analysis, the fact that to get the semigroup is related to the resolvent, right? So the semigroup, so you are writing down the formula here is the semigroup, meaning that psi hat of t, you have to do the resolvent. You have to solve the resolvent, right? Okay. So this is a very important formula, and immediately it puts us in ODEs. So to understand all these things, you have to understand this kind of ODE, but it has singularities. And clearly what we have to do is you have to understand this ODE as a function of C, right? As a function of C, the spectral parameter. And then clearly some kind of limiting absorption lemma should come into the game, because you want to send C to the range of u from above and below, right? So the good thing is that there is already a work of Wei, Zhang, and Zhao, where what they did at that time was they were trying to prove implicit damping estimate. So they have a paper where they study this kind of, where they study the ODE, but there they were interested in just estimates. In what we have to do here, we have to go one step further. We have to have a very good representation formula. So we are not happy with just estimate, but we have to have a very good representation formula to construct the wave operator, because we need the wave operator for the nonlinear term also. But somehow we can use this limiting absorption lemma of Wei, Zhang, and Zhao. In their work, they were already getting the as I said, the implicit damping, the fact that, let's say, the first component of the velocity decays 1 over t, the second component decays 1 over t squared. How do they get that? They get that by integration by parts. So you have to integrate by part on C in that formula. So you have to integrate by part in C once or twice, right? To get the 1 over t decay of V1, you integrate by part once. To get the 1 over t squared decay, you integrate by part twice. But that already, this kind of things already appeared in their work, so we can use that, this. But just to understand better what's happening is that even if, right now you have that equation, it has the alpha. The alpha appearing there makes it a little bit more hard to, but if you remove the alpha, let's for now, to simplify, let's just remove the alpha, because what happens if you remove the alpha, you can have an explicit solutions. You know what are the explicit solution of the ODE. So then if alpha is 0, you can see that U minus C solves the equation. And then, I mean, if you have one solution, you can get the second one. So you get U of Y minus C is the first solution, and the second one is U of Y minus C times the integral of 1 over U of Y minus C squared, right? So you know what are the two independent solutions of your homogeneous ODE. And so that's how you can get exactly the whole solution. So you have the first term is the inhomogeneous part, and the second line is the special solution, the solution of the homogeneous equation. So at least it shows you when alpha is 0, you can find exactly what is the solution. And you can see the kind of singularity that can happen is this log singularity. You get this log singularity when C approaches the range of U. And that's exactly, I mean, there are these singular integral kind of things. And it shows you here what is the, even how also we proved the 1 over t and the 1 over t square decay, right? Okay, so this in a sense, after some work, allows us, I mean, like, one has to write down exactly this psi minus psi plus exactly in terms of the omega 0, right? You have to write it down exactly in terms of the omega 0. And now you take that formula that is valid for all t, and you take it at t equals 0, right? Even though it is valid for, I mean, it is valid for all t, but you take it for t equals 0. So then you are able to write down this kind of representation formula, and that turns out to be very useful in constructing the wave operator. Okay. So maybe I can just make a small summary of this linear part, so if you can see the kind of steps we did the linearization, we used some function analysis using the spectrum. So then there was applying the resolvent, there were some ODE results. The behavior of the ODE has to do, the behavior of the ODE is related to the regularity of that kernel, right? And now the next question, but I think I don't have time, and that was, I was thinking that I will stop here, is how to apply that to the nonlinear problem. I can just show you the linear part of it. I mean, I was planning just to mention the linear part. The linear part is how we get rid of the non-local term, right? So, but here the thing is that we have a non-self-adjoint operator, right? So when we deal with Schrödinger with the potential, we use the wave operator, but in that case we have self-adjoint, usually self-adjoint operators. Here we have non-self-adjoint operator, but still it will still work, right? It still works, meaning that by applying the wave operator, that comes from that formula exactly gives us the wave operator. By applying that formula, we are able to get rid of the non-local term in the equation. So, and it has that formula. Okay, maybe I'll stop here, I think. Thank you.
Thank you. Okay, only a short question.
For your methods, what would you consider to be the main problems to apply to 3D case, for instance?
Okay. Right. Now, for 3D, I mean, we have results in 3D. So there is a literature I mentioned at the very beginning in 3D. In 3D, the linearized operator has another feature, which is the so-called lift-up effect. Lift-up effect, this is a very known phenomenon in physics. I mean, it appeared at the linear level when I wrote, if I go back to the very beginning, so there was, so the U2 there, minus U2. The minus U2 in this equation, this is a feature of the 3D. You don't have it in 2D. In 2D, that term disappears. So in 3D, I mean, it doesn't give anything. Or at least when you write it down in terms of the vorticity, it disappears. In 3D, that terms gives you a linear growth. So when you linearize around wet flow in 3D, the solution has a linear growth. Now, linear growth is not exponential growth, but it is still linear growth. And that is the main difference between 2D and 3D. In 2D, we are able to get implicit damping directly. For one component of the velocity decays 1 over t, the other one decays 1 over t squared. That doesn't happen in 3D. In 3D, you have linear growth. Now, the linear growth, the only way you deal with it is that you need the viscosity to help you, right? So in 3D, we don't have a similar result. I mean, we don't have a result that says that you can perturb 3D Euler. You can perturb 3D Euler and get decay. There's no such kind of result, right? Due to that term, and that's why, like in 3D, these are the results I mentioned here. These results, like in 3D, you need gamma is 1, right? You need the perturbation to be of the size of the viscosity, okay?
Thank you.
Okay, time is up. And let's thank the speaker again.
Thank you.
Colleagues, thank you, Nadir, for your wonderful talk.
And colleagues, we are doing excellent job. Thank you for your understanding and support. We are behind schedule, but we want to compensate that. So I've just sent an email to Professor Susanna Terracini. She agreed. We're going to start our talk at 11:50. So we have for coffee break around just more than 15 minutes. We're going to compensate it. 11:50, colleagues. Colleagues, we have very short time for coffee break. So I kind of ask you to, colleagues, we have very short time for coffee break. So I kindly ask you to reach ballroom left, yeah. And we're gonna return in 15 minutes. Paula, about coffee break? All right.
А, нет, ты что? А. Дана, возьми кликер. У нее.
Ильдар.
Раз, чек.
Ильдар, кликер там, да?
Кликер? Нет.
Амо.
Да, кликер нет. Да, он здесь.
Можешь поднести сюда? Просто уже не нужен будет там кликер.
Хорошо. Так. Скан куда?
check. Hey.
Hi.
Hello.
Hi.
Hello. Unfortunately, we're very much behind the schedule, and the next talk is by Susanna Terracini, dall'Università di Torino. And also, unfortunately, she is ill, but she agreed to give this presentation nevertheless.
Okay. So can you hear me?
Yes, we hear you well.
Okay. So now I will share my screen. And I'm sorry not being able to be there in person with you. Can you see my screen?
Yes, it's about rotating spirals in segregated reaction diffusion systems. Thank you.
Okay. So, first I would like to thank the organizer for this very kind invitation and express my regret not being able to be there in person. Sometimes it happens that one has, what happened here? Wait. I have to start maybe again with the share screen. Okay, on the screen here. Okay, so what I'm going to talk about today are some recent results and some little history about some special solutions appearing in reaction diffusion system and in a highly competing regime. And to start with, I would like to recall a principle which is often referred as Gauss' law of competitive exclusion, which is very popular in population dynamics, and that states that when you have two species that compete for the exact same limited resources, they cannot stably coexist at a constant population levels. Here you can see the statement, and so the idea is that when one species has even the slightest advantage over the other, this one will eventually dominate, and the second one will be finally go to extinction. So if there is even a very, very small advantage of one population, there will be extinction of the weaker competitor. Well, as sometimes happen to such statement, well, first is not a law, it is even, and I will try to prove that it's actually a false statement. And also, in fact, Gauss didn't state it at all. Okay, so this was, in fact, a kind of popular and easy statement attributed to Gauss. Okay, now how does can one see or can one translate the Gauss law into mathematical models of population dynamics? Well, the idea is that when the environment is constant, is homogeneous, and the two population obeys the same laws, one species will inevitably exclude the other. For which initial condition? Let's say for almost all initial condition, but a small zero measure 1. If we look, for example, at very simple systems of ordinary differential equation, like Lotka-Volterra with the competitive interaction, in fact, one sees this is a very easy computation, that it can have at most one stable equilibrium. One stable coexistent equilibrium means that all the two populations are not serious. This all the other initial data will eventually lead to extinction of one of the competitors. Okay. Besides mathematics, the Gauss law also have a kind of philosophical counterexample, which is natural, where in fact we see great diversity patterns in life, where competing populations actually find their way of coexistence in maybe sometimes by taking advantage of different geometries and different patterns. Okay, so what may be the mechanism, also the mathematical mechanism that allow coexistence in competitive environments? So we should put into play some more mathematical elements. First point is to go to increase the dimensionality. So to go from ODEs to PDEs, and to add in the play also diffusion, spatial diffusion, I mean, and also possible difference in the behavior, spatially or temporal heterogeneity, the multi-resource competition, and all these elements may increase the probability of coexistence. So the idea in this talk, I will actually try to prove that there are also increasing the number of competitors from 2 to 3 or more is an element that will increase the likelihood of coexistence with different patterns. Okay, so let's go and let's look at the simple model of competition diffusion system. So we have two competitors, two densities, U and V. Each one has some random dispersal, which is, let's say, modeled by the coefficient du and dv. Then they have some intrinsic growth rates, which are Ru and Rv. And then there are interactions, both interspecific and intraspecific interaction, which are expressed by the coefficients alpha, beta, gamma, and delta. Okay, the minus sign here stands for the competitive. Excuse me? Okay, can I continue? Okay, so the minus sign here, especially in front of beta and gamma, accounts for the competitive nature of the interaction, because the population V opposes to the diffusion of population U, and population U opposes to the growth of to the diffusion of population V. Okay. Now, for this type of, then of course we add some boundary condition, usually for let's say isolated system of population, the no flux Neumann boundary condition will be a reasonable one, but also Dirichlet or other type of conditions are fine. Okay, now. So in this case, the statement is that there are no stable solutions, but the semi-trivial ones, means that one of, let's say, the competitive exclusion principle was proved when the domain have a simple geometry. For example, it is convex space, is convex domain, but another side of the research was to prove that when some niche are created by the geometry, by the diffusion, and so, then there can be stable steady states that accounts for coexistent states for the population. Okay, and of course one can look to a full competition system, but also to prey-predator systems, what are sometimes called the Lotka-Volterra type systems. And in that case, there is a very, very general result by Nimura about the fact that solution, and this is also another issue which is related, solution will become asymptotically constant, so spatially heterogeneous when time increases. This is not exactly an exclusion principle. It is a different type of principle that in any case affects the heterogeneity of the distribution of population, and which also has to be considered in the. Okay, so in the analysis. Okay, what will be our point of view? We think that the competition, so the interspecific competition coefficients becomes very large. Okay, so we try to make some asymptotic analysis when the competition rate go to infinity. And in this case, there is a known phenomenon which is called phase separation or segregation that states, in fact, that a local in space exclusion principle. So if we have a solution, we have a family of solutions when the competition increases, which stays bounded, then the densities cannot coexist at the same point. So there will be some limit which is segregated, where the density have disjoint supports. Okay, this is in fact a phenomenon that happens in many cases, in many mathematical models where competition occurs. So not only in population dynamics, but also in the ground states of multi-component condensates and many other many other physical or application contexts. So what can we try to? How can we try to approach this problem? Well, first, trying to develop an asymptotic analysis when at high competition regime. Then we try to analyze it, to find and to discover some simple solutions, maybe having some self-similarity. Then when there are this phase separation, this segregation, there are boundaries, interfaces appearing. And also we can try to glue different solutions across the interfaces by building new type of solution. Okay, now let me show you some pictures. Okay, now we consider competition diffusion system of 3 components with large and symmetric competition rate. This means that the interspecific competition terms has a quadratic form, and the aggressivity of one species toward the other is the same, is symmetric. Okay, and now here we fix some boundary data and we plot the level set of all the 3 components, assuming that they have already reached a stationary configuration. So the system now is it's supported by some boundary threads, and what we see is in fact that there are interfaces here, the dark blue part, which are rather regular arcs meeting at one triple junction in a rather regular manner. But when we look at the same type of solution, when the interspecific competition rates are different, so the aggressivity of one population or the other becomes non-symmetric, then we see that the nodal, the no-one zone, so the zone where the 3 populations are very scarce, starts to have a different shape. And in fact, we proved in a paper that they will not meet in a regular manner with definite tangents, but they will draw asymptotical logarithmic spirals. Okay, so let's look at closer to the structure of the system. Yeah, I'm omitting here boundary condition. If you like, you can always take Neumann boundary condition, which are very popular in this context. So we have a term modeling the time evolution, the space diffusion. Then there is the internal reaction, because and this is usually assumed to have a logistic form. And then there is some competition. Competition terms may have different forms. Here we have the simplest one, which are quadratic, involving these interspecific competition rates that can be either symmetric or non-symmetric. Okay, the internal forces can be assumed to have a logistic form. Okay. We now will consider the case of all equal diffusions. Of course, having a different diffusion will make the problem even more complex. We assume that some coefficients Aij are given, and that the full interspecific matrix of coefficients is a fixed one multiplied by one single parameter, which will eventually go to infinity, in a way that the competitive interaction becomes the prevailing, the stronger term, and this system is falls in the class of singularly perturbed systems. Okay, so our questions are whether there are spatially homogeneous solutions, what happens when the competition parameters go to infinity, what are the common features of the family of solutions, the family with respect to data, are there segregated limiting profile, what are the features, and what is the geometry of the interfaces. Okay, of course, everything, most of the non-trivial examples of coexistence states may be related to special geometries of the domain. There have been results about this. For example, dumbbell type domains, which are somehow favoring the creation of niche, may come into play. But this is not what I'm going to talk today. Okay. And I would like to talk about how we can obtain non-trivial solution with non-trivial spatial patterns with three competing densities, and how spiraling solutions come into play in this case. Okay, so we go from 2 to 3 solutions, and we consider a system of equation which has a special structure, because has some cyclic symmetry. This means that when I exchange, when I cyclically exchange the triplet 1, 2, 3, I actually reobtain the very same equation. Okay, so they have a common population 1, 2, 3. They are somehow equal. They share the same growth rate. The competition intensity will be the same. There is an asymmetry between two neighboring diffusions, but this is cyclically symmetric. Okay, and then we stay as a domain in the unique disk, and we add either Neumann or Dirichlet boundary condition. Okay, and then we look at solutions which have some special symmetry. Especially, they are invariant under rotation, in the sense that when I rotate the motion in time of each component is actually the result of the composition of three fixed profiles with a rotation in time t with angular velocity w. Okay, and when we insert these ansatz in the parabolic system, then we obtain a system which is not time depending anymore, because time dependence has been exhausted by the fact of staying in a frame which rotates uniformly, and the diffusion operator changes, and we see the appearance of one gyroscopic term of this time. Okay. Now we try to solve this system of three equations, and we wish to find authentic rotating waves for the system. So, because to be a rotating wave, the triplet must first depend on the angle effectively. Otherwise, okay, if U1, U2, and U3 are only depending on the radius and not on the angles, this system trivializes. Okay, so we wish to find solutions which have an effective dependence on the angular variable. Okay, now let me see if I can open this. Oh, too bad, I cannot. Let me see if I can do it in a different way. Sorry, this is a little technical mistake. Should be a. Let me see. Okay, let me see if I can show you this. Okay. So in this video, we see the creation, the appearance of such spiraling waves. So here we have the three components, U1, U2, and U3. Okay. And they are very strongly competing. So you see that they occupy three distinct regions, basically of the domain. So they are almost segregated. And what I'm showing you is in fact the solution of the parabolic system. So we see that the system itself creates a stable rotating wave, okay, which is so is not only one possible solution, but it's probably, we conjecture, a stable solution. And when we start from different initial conditions for the three densities, then we see that such spiraling waves appears maybe in a multiplicity, and they appear to be stable, to be there, to persist for long times, creating very nice patterns. In this case, we always chosen some symmetric initial condition for the three population. So the pattern of spirals appears to be symmetric, but one can do this game for any type of initial condition, and more or less the result will be the same. Okay, so the idea is that not only we can prove existence of such rotating waves, but such rotating waves are actually some stable patterns which have an influence on the whole dynamics of the system. Okay, so first, but now we have to work hard to prove existence of such rotating waves, which are, as I said, actually thought as stationary solution of the time-dependent parabolic equation in a time-rotating frame. Okay. So at first, one remark which is important is that the operator, this elliptic operator, is not self-adjoint. So the spectrum has complex eigenvalues, and these complex eigenvalues will be crucial for bifurcation. And we can prove that, in fact, the spectrum consists of complex number whose real part are the Laplacian eigenvalues with boundary condition, and the imaginary part are just multiples of the frequency. Okay, and now we wish to use non-radial eigenfunction for bifurcate from the trivial solution, which exists, which is a constant solution where all components, all components have the same value. Okay, and then when we look at, this is a result obtained in collaboration with Zai-Zong Li. So when which are the bifurcation parameters? Okay, in general, we have 4 parameters: mu, which is the internal growth rate, alpha and gamma, which represent the asymmetry of the interaction, and beta, which is the parameter that governs all the competition. Okay, so if we wish to bifurcate, we have to choose 2 of these 4 parameters. Sorry, I forgot. And we also have the angular velocity omega. Okay, alpha and gamma actually accounts for the one single parameter. We choose as bifurcating parameters mu and beta. Then we find this bifurcation values, which are, you see, show that asymmetry plays an important role. The integral k should be of the form 3m minus 1, so to be 2 modulus 3. We can also obtain let's say a local expansion of the bifurcating branch close to the unique positive constant solution. We may also choose as bifurcation parameters instead of mu and beta, omega and beta, and then we find also some parameters, some other values. Let me note that this is important because we wanted to address the problem of high competition rates, that beta is allowed to be very large, basically when the local growth rate approaches a value which is the double of an eigenvalue of the Laplacian. So even very high values of beta are allowed. Be careful on the other hand, because when beta is very large, the constant solution becomes very small, and so we are actually finding small solutions. So this result is, is the first existent result for rotating waves, for non-trivial rotating waves in this context. We also have the expression of the expansion of the tangent of the bifurcating branch emanating from the constant solution. But the bad news is that we actually are finding unstable solution, in the sense that the constant solution is unstable for large values of beta, and we are staying in a neighborhood of 8. Okay, so the proof of the theorem is that we have only one non-trivial solution. We can apply some multi-parameter bifurcation theorem, for example, one by Kielhofer, and by linearization, and applying the bifurcation theorem, we find non-radial and symmetric solution. Okay. Okay. So what about instability? Well, instability is not satisfactory when we compare with our numerical experiments that show that the spirals are supposed to be stable for large values of beta. But in the context of bifurcation and also of other consequences of the existence of rotating waves, but instability is the key opening some kind of central manifold type of analysis which has been carried out by Sunstein, Steele, and Wolf. Okay. Then we may also have a theorem about existence of rotating waves for given boundary data. And in that case, the proof takes advantage of topological fixed points, and these are also can be found. Okay. Now, let's say that this ends our first proof about the existence of rotating spiral waves in a logistic type models. Okay, now I would like to go back to this rotating wave answer, to an earlier result by Murakawa and Ninomiya, which observed, in fact, the presence of rotating waves, of rotating patterns, actually, in parabolic system with three competition and large asymmetric interspecific waves. And I will now report on a different construction that we have done recently to enlighten this type of phenomenon. Okay, now let's look at the reaction diffusion equation, as I said before, and assume that beta goes to infinity, and as I said, the densities will tend to segregate. Okay, so to convert to a limit having disjoint, where the component has disjoint support, and okay, now we play some easy algebraic game, and we consider what happens to each component when I subtract this linear combination of all the other. I can do this for the densities and for the reactions, and then these inequalities, with these differential inequalities, will be brought to the end of the limiting procedure when beta goes to infinity. So now we have components ui and uj which have disjoint support, okay, and the validity of these inequalities incorporates the transmission condition at the interface. Okay, so now we have to think of having this interface that move in time, okay, and they are the motion is driven by these differential inequalities. Okay, and now again we insert in this game the spiraling wave ansatz, the rotating wave ansatz. So we imagine that each of the ui, of this limiting ui, is the composition of some fixed profile with a rotation of the x variables. We again go to these inequalities. We now will involve not the heat operator, but this elliptic non-self-adjoint operators that we have found already. And we imagine to work on the ball or the complex plane or whatever. Okay, but now we fix our attention on the nodal domain. So the nodal set, the interfaces, the states where the VI, these profiles, are 0. Okay. So again, here we have two figures that show these nodal lines, these spiraling nodal lines, okay? And here we have actually two different spiraling phenomena. One is close to the center of rotation and is due to the asymmetry, to the Sol asymmetry. And in fact, in the difference between the two pictures is in the angular velocity. You know, in one case is 3 and the other case is -3. Okay, so the difference of the angular, the positive angular velocity here has an effect on the nodal line close to the boundary, which is different in the two figures, as you see, while close to the center of rotation, there is the same type of rotation. Okay, so be careful that here spiraling effect comes from two different reasons. Okay, And now we consider a special case, that is the case when reactions are linear and all equal. Okay? So this is different from before, where the reaction had a logistics or quadratic, so they were linear, close to zero, but then with a parabolic graph. Here we only have linear, exactly linear reaction. And then now we play this game, we fix some boundary, segregated boundary trace on the boundary of the ball, which are have some reasonably compatible with phase separation behavior. And well, in general, we are fixing the center of rotation. So actually, we cannot imagine to have a solution for all traces, okay? Because different traces could have some junction which are not at the origin. So when we fix the position of the common junction, we should, in fact, select some high codimension set of traces. Okay. Now we consider for the moment the set of traces. We fix some normalized traces, and then we multiply by some multiples. Okay. So we have parameters Si, which are the multiples of each, the multiplier of each element of each single trace. And also we introduce this parameter, which is accounts for the total asymmetry. You see, you take the total asymmetry of the system. And then we have this result, which we have obtained in collaboration with Ariel Saralt, Gianmaria Restini, and Alessandro Zilio, that says that if mu is smaller than pi squared, and we take admissible traces, then there exists exactly one vector multiplier that gives rise to a rotating wave solution. And this rotating wave solution has this expansion when r goes to 0. This expansion, you see, is important because it gives us the asymptotics of the nodal lines, the interfaces. And these interfaces are, in fact, asymptotically logarithmic spirals. Okay, theta is a multiple of the logarithm of the radius. Okay, and well, the order of vanishing is related with the number of components and this asymmetry. And if there is invariance under rotation, then the solution will be invariant under rotation. And as I said, the interfaces, when alpha is different from 0, are asymptotically logarithmic spirals, but when alpha is equal to 0, the nodal line will go with interfaces, will go with a definite angle. Okay, and with the same type of analysis, we can also treat the case of homogeneous boundary condition, the case of entire solution, and also, so and in this case we have to avoid a discrete set of resonances that will, not only to avoid. If we wish to have homogeneous boundary condition, then we will stay in a set of parameters which satisfy some resonance condition. And this is a discrete sets, and we can find also solutions which are satisfy homogeneous boundary condition, entire solution, and also Neumann boundary condition. So how does the proof work?
Professor, 5 minutes to conclude.
Yes. Okay. So let me just make the final result. The final result is that with this construction, we could prove the existence of spiral waves for the heat equation. Okay, so of solutions that of entire solution with, of course, some definite growth rate at infinity, having 2k nodal regions for every k. So this is more or less the pattern of this of the zero set of these eternal solutions of the heat equation with k nodal domain. Okay, that's all. Thank you very much for your attention.
Thank you. Any questions or comments, please? No? Okay. Thanks a lot.
Thank you very much, and I wish you a very successful conference. Bye-bye.
Thank you so much. All right, colleagues, now all we should head to the general group photo place. It's entrance, but different entrance. It's so-called Turan entrance. So this is the exact opposite entrance. So you guys use this mega site, Kabamba entrance. So this now our volunteers, they will help you. Please group photo. And for lunch, I recommend to stay on campus. On campus, there are many places to have good lunch. There's Turn restaurant, Kunde restaurant, some other restaurants close to hotel. There's another restaurant. It works, I think, 24/7.